Hello ladies and gentlemen, and welcome to the notes for Intro to Polynomials. I'm going to start off with a definition. A polynomial, p of x, is a power function, and it's usually in the form of p of x equals a sub 1 times x to the n plus a sub 2 times x to the n minus 1 plus a sub 3 times x to the n minus 2 plus, and it keeps going until you just have the a sub n. Now I'm going to explain what all this subscripts and superscripts mean. Basically, a sub 1, a sub 2, a sub 3, these are all just constants. These are all just numbers. They could be positive, they could be negative. Of course, x to the n, that's just x to any power. When you write a polynomial, though, we usually write the polynomials in descending order of exponents. So in other words, your biggest exponent is usually in the front. And then I'm going to show you an example of this real quick, and I'll just write it down here. And then when a polynomial, as the exponent gets smaller, eventually goes to 0, you're just left with a constant, and that's that a sub n. Okay. This is just nomenclature, way to write things so that it's more universal. Math has to be universal if you're in China or Italy or wherever it's at. People recognize, oh, that's a power function, that's a polynomial. Let me give you an example of a typical polynomial that you're going to see in this class. Basically, we'll have stuff like, let's see, p at x equals, well, I don't know, negative 2x to the fourth plus 3x to the third minus or plus 8x squared minus 4x to the 1, or you don't have to write it. And finally we'll get to something like 6. Again, the a sub 1, a sub 2, a sub 3, that are the coefficients in front of the x. And of course you see my exponent goes down by 1 each time. That's a typical polynomial, and we're going to be dealing with these polynomials, what their graphs look like, how to find the solutions to these graphs, and eventually we're going to start talking about some calculus stuff, and it's some intuitive calculus stuff that most of y'all probably already know. But yeah, this is typical of what you're going to be seeing, ladies and gentlemen, in this section. All right, let's go ahead and move on, because I want to start off. The thing is, when we talk about polynomials, it is called an exponent, but I also refer to it as a degree of the polynomial. In other words, the degree of the polynomial is the highest exponent that you have. We dealt with degrees of polynomials when we were doing asymptotes. Now we're not doing asymptotes, so don't panic. I'll be saying the word degree, and the degree means just the highest exponent. Degree 2 polynomial. Y'all should be very familiar with this. It's called a quadratic. Matter of fact, in Algebra 2, we spent a whole lot of time on quadratics, factoring them, solving them, using the quadratic formula, solving them using, square roots. And matter of fact, even did some quadratics this past time where we actually solved them in the calculator. Ladies and gentlemen, what we're going to do is we're going to talk about this as a polynomial now. So it's like, well, what's the difference? The difference being is that how what we learned about quadratics translates to higher degree polynomials. So for instance, let me grab this right here, or before I do, this crosses the x-axis in two places. These are called the roots, right? These are called the roots. And so what I'll do is I'll say, okay, here's one root here and here's another root here. And the way we would write this is we'd write, oh yeah, y is going to equal, it's going to be x, and you know what, I'm going to change the color in a second, but x plus, let's call that for no other reason. Let's call it M. So this crosses at M over here. And then I'm going to change the color of this one. It's now red. It's going to be X minus N. Okay? Now, what I'm saying is, over here, the orange one, and this orange one right here, this crosses right here at M. Say, well, that's plus. Why is it on the negative side? Because if it's inside parentheses, you always do the opposite. Okay? And then this one, minus N, it's right over here on the positive side. Well, remember, opposite of negative is positive. So whatever's inside, we talk about it as the opposite of it. Y'all have seen stuff like this. We've actually multiplied stuff out like this. But these are the two roots. Okay? But, there's a really big but here. That's if there's two distinct roots. Sometimes quadratics do not have two distinct roots. Matter of fact, in Algebra 2, we talked about this. Sometimes quadratics, and I'm going to move that arrowhead real quick. Sometimes quadratics, ladies and gentlemen, they only have one root. They only have this one root right here. Okay? And that one root has a special feature. You see a couple of things. When we write it, it's going to be y equals, we called this x minus n, right? We called it later, but it hits it twice. In other words, at this root, the graph comes down, touches the x-axis, and then goes back up. That's what happens anytime we have this kind of squared thing like that. But this only has one root. It only touches the x-axis at one place. I know some of you are thinking too. You're going, hey, Mr. Martinez, last year in Algebra 2, I remember our teacher telling us something about quadratics don't even have to have roots. Quadratics could just float above the x-axis and not even touch it. Yeah, that's true. And if it doesn't have any roots, I don't really necessarily know what the equation is. I'd actually have to do something to find that equation, because this doesn't have any real solutions there. So, again, when we go back, this has two roots, or it could have one root, or it could have no roots. That's a degree 2 polynomial. It could have two roots. And again, I'm using the word roots as an x-intercept. It could have one root, or it could have zero roots. All right. Now, let's look at a degree 3 polynomial. Y'all are familiar with degree 3s because over here on the left-hand side, this has been the cubic equation we've been dealing with, and we dealt with it last year in Algebra 2. These cubic equations have the form y equals ax to the third, bx to the second, plus cx plus d. This particular one right here has one root, and it's where it crosses the x-axis. And this is, I drew this on purpose because this equation is y equals x cubed. We have the root at 0, so we don't have to add or subtract anything. However, ladies and gentlemen, I know that y'all understand that I could shift this around. So in other words, I could have a root at a different place. Matter of fact, if I shifted it this way, how would that change my equation? Well, the way it's going to change your equation, ladies and gentlemen, is this way. Oops. Now that I've shifted it over this way, it is going to be x plus, let's say that's m, to the third power. Okay? So, well, what if we moved it to the other side? So let's do that. Let's take this root, put it over here, and move our graph, and put it over here. Well, the way that's going to change things, that just means, oh, that's going to change that to minus, because it's on the right side now. And we've dealt with things like this before. You may not remember shifting cubics, but that was laying the foundation of what we were going to do in here. Now, not all cubic functions look like this. Matter of fact, most cubic functions we're going to deal with are going to look like this. It looks like the letter n, right? I want you to notice that this cubic function has roots here. It has a root here. And it has a root here. Okay? And the way we would write this equation, we'd simply say that y is going to equal x minus, or I'm sorry, plus, we'll say m, because I've been using the letter m. And then the next one, ladies and gentlemen, is going to be x plus n, right? Because that's the next one. It's still on the left-hand side. Then I have my third root. And my third root, ladies and gentlemen, is going to be written as x minus, I don't know, we'll call it p. Just because I'm going in alphabetical order. But yeah, notice that the yellow dot is on the right-hand side, so we get a minus p there. And this is what this equation would look like. And of course, we could multiply it out. Now, the neat thing about cubic functions is that it could have 3 single roots, and I'll talk about what a single root is in a second. Or it could have different versions of this. And I want to show you something real quick. Let me back out of this real quick. So here's what I'm going to do. Oops. I'm going to take our cubic function, and I'm going to grab it, and I'm going to move it up like this. Or you know what? I think I'll move it down this time. Yeah, I'll move it down this time. Yeah, well, it's a lot nicer. I'll move it down here. Notice now, still same function, but this time, ladies and gentlemen, my cubic function touches right there, and it touches right here. Say, well, it only has 2 roots. Nah, it has 3 roots. It just so happens to have a double root and a single root. If you have a double root and a single root, you still have 3 roots. And again, I'm going to explain double roots and single roots in a second, but let's write this equation real quick, because that's pretty much what we're trying to do here. So the first part of it's going to be y equals, then I've got this x plus m, but it's a double root. And then I've got the yellow one, which is a single root, and that's going to be x minus n. So you can see it would still be to the third power if I did all the multiplication. So I know what some of y'all are thinking. Saying, well, could it have a triple root? And that's it. And that's exactly what this is over here. But I'm going to show you, this is just the basic parent graph. I'm going to show you what this would look like if it had a triple root. So let's do that real quick. Let me try to. Oh no, that's interesting. No, no, no. This is how it would look if it had a triple root. I'm being silly. All right, so there we go. Sorry about that. I had a brain fart real quick. But basically, that's what you would have. You would have a double root and a single root, or a triple root, and that's what these graphs would look like. Of course, I could flip them upside down. That's another thing we could do, but we'll talk about all that later on. But for right now, I just want you to get familiar with what these graphs could look like. Let's move on to the next degree, which is degree 4 polynomial, and that is a quartic. Now, it sounds like quadratic, but it's a quartic. Quartics are the form y equals ax to the fourth power. Ooh, I put ax to the second power, but it should be ax to the fourth power over here. Ax to the fourth power plus bx to the third power plus cx to the second power plus dx to the 1 power plus e. Okay, so these graphs will look like this. Now, some of y'all are saying, hey, this first graph looks like a quadratic. It's true, it does look like a quadratic. However, down here in the bottom, it's a little flatter. It's not very distinguishable by the eye. We'll see it with the calculator later on. But just like the quadratic, this could have two solutions. Okay, it could have two solutions. Or it could have, oops, sorry, one solution, right? Or it could have no solutions, right? So, well, how's that even possible? Well, we'll talk about it. We'll talk about it because it does get kind of complicated when you talk about quartics. The next form I want to look at. Oh, and let me write the equation of this quartic right here. This quartic would be, and I'm going to put it up like this. This is how I wanted to draw it at the beginning. Doot, like this. Okay, this is what the quartic would look like. And let's put my dot right here. Okay, this quartic equation would be y equals x minus or plus m to the fourth power. Again, notice at the fourth power it just touches and it goes back up. Okay. If you had a polynomial that looked like this, however, you'd see it has a dot there. It has a root here. Sorry, I'm having a hard time with my mouse right now. It has a root right there. It has another root here. And finally, it has another root there. Okay? Now, since it has four roots, ladies and gentlemen, the way we're going to write this equation, and I wish I had enough room. I think what I'm going to do is I'll erase the top of this thing right here. Erase the top of that right there. And I'd write it this way. It's going to start off y equals x plus m, right? That's a single root. And then the next one is x plus n. The next one would be x minus, I don't know, p. And then the last one, of course, is going to be your x minus, I don't know, we'll just say q. Q, that's a q, not a 9 or anything. The letter q. So you see you have four roots, and that's where they cross the x-axis. Notice that the signs do change inside the parentheses. Okay, so what's this third graph, and why does it look kind of weird? And is that a quartic? It's a quartic. This one happens to have a triple root. And that triple root is right there. Notice through the triple root it does something funky. It kind of looks like a cubic graph almost. And then it has another root on this side, which is a single root here. And the way we'd write the equation for this, we'd start it off with y equals x plus m. But this one's a triple root, so it's to the third power. And this one is a single root. This would be x minus n. So if I have a triple root and a single root, that would give me 4 roots. And again, the roots, you could also call them solutions. You can also call them the zeros, or you can also call them the x-intercepts. Why they have so many different names is because it just depends on what you're doing. If you're trying to do the graphs, they're x-intercepts. If you're trying to find the solutions, they're called zeros or solutions. But basically, they're rooted on the x-axis, and that's where the roots go. What I didn't show you in this particular scenario, I showed you 4 single roots. I showed you a triple root and a single root, and I showed you a quadruple root. What I didn't show you was 2 double roots. I'll show you 2 double roots later in some of the examples we'll have. But again, what are these single, double, and triple roots that I'm talking about? I mean, it seems like I just threw that out there. The next slide is going to be talking about that, and then we'll get into some examples when you come into class. So let's look at the types of roots that we have. Now, when I talk about a single root, and that's going to be this first one here, this single root, polynomials, the graph will just go right through the single root. So in other words, let's say I had a single root here. It will just go straight through it like this. That doesn't change it, doesn't do anything. Now, this next one is a double root. When I get to double roots or quadruple roots or sextuple roots, any even number of roots, what's going to happen is we're going to approach that root. We're going to get real close to it, and then when we touch it, we're going to bounce off of it. So you always bounce off of double roots or even number of roots, right? So it's going to go straight through the single root. It's going to bounce off the double root. And when I get to the triple root, ladies and gentlemen, it's going to do this thing which I'm going to call an inflection. Okay? So it goes through the single root. It bounces off of a even root, and it does kind of like an inflection, kind of changes direction. An inflection through a triple root, quintuple root, septuple root, any multiple that's an odd multiple other than 1. And by the way, since this has a single root, a double root, and a triple root, if you add all those together, this has a degree 6. And that's another thing. A degree 6 polynomial. Okay, so this is what degree 6 polynomials could look like. And we will be looking at some degree 6s. I think the highest degree we'll get is maybe 7 or 8. But those will be really interesting to look at, and just things I want you to see. I'll be honest with you, the highest polynomial you'll ever probably deal with is going to be a degree 4 polynomial outside of high school. But inside of high school, we're just trying to get a little bit deeper and see what these things do every time they have different types of roots and the different combinations of roots you can have. And we'll be investigating all that later on. But take these notes, write them down, and we're all going to calibrate our journals starting right now, because we're going to, it's a brand new 9 weeks. Okay, thank you for watching, and don't forget to like and subscribe to this video and my channel.